Hello students, welcome to Educate. Today we are going to start the chapter Waves, that is last chapter of class 11th physics. You have already studied about different type of waves. So here we will study about mechanical waves. Mechanical waves like sound waves, they need material medium to propagate, and there are electromagnetic waves that don't need any type of medium to travel, and speed of electromagnetic waves is 3 into 10 power 8 meter per second. The same thing is given here, 299,792,458 meter per second. This is accurate value, right? So here some more information is given. The third kind of wave is the so-called matter waves. They are associated with constituents of matter, electrons, protons, neutrons, atoms, and molecules. They arise in quantum mechanical description of nature that you will learn in your later studies, though conceptually more abstract than mechanical or electromagnetic waves. They have already found applications in several devices basics to the modern technology, like matter waves associated with the electrons are implied in electron microscope. So we will study about them later on. Here, if you observe this diagram, there are three springs. So a collection of springs connected to each other. The end A is pulled suddenly. Here we pull it, generating a disturbance which then propagates to the other end. And here another term is given. Pressure is force per unit area. So there is a restoring force proportional to the disturbance, just like in a spring that you have studied. Then if you remember, crest and trough in case of longitudinal waves, and compression and rarefaction also you have studied in. So here we will study them one by one. Rarefaction means there is very less pressure and molecules are far apart, whereas in case of compression molecules are very close, that is there is higher pressure. Now pulse is so near. Pulse, a wave of very short duration. When a pulse travels along the length of a stretched string next direction, the elements of the string oscillate up and down. So that is very clear. Then here also you will see harmonic wave. So here sine wave or cosine wave. A harmonic sinusoidal wave traveling along a stretched string is an example of transverse wave, and element of the string in the region of the wave oscillates about its equilibrium position perpendicular to the direction of propagation of wave. So motion will be like this and the wave will move like this, right? So these are basic things. Now here compression and rarefaction is shown. Longitudinal waves like sound generated in a pipe filled with air by moving the piston up and down. A volume element of air oscillates in the direction parallel to the direction of wave propagation, right? So what you have observed, in case of transverse waves, the particles oscillate perpendicular to the direction of wave propagation, but in case of longitudinal waves, particles oscillate along the direction of wave propagation. There are some more waves, like waves on the surface of water are of two kinds, capillary waves and gravity waves. The former are ripples of fairly short wavelength, not more than few centimeters, and the restoring force that produces them is the surface tension of the water. So we are talking about capillary waves. And gravity waves have wavelengths typically ranging from several meters to several hundred meters. The restoring force that produces these waves is the pull of gravity, which tends to keep the water surface at its lowest level. The oscillations of the particles in these waves are not confined to the surface only, but extend with diminishing amplitude to the very bottom. The particle motion in water waves involve a complicated motion they not only move up and down but also back and forth. The waves in an ocean are the combination of both longitudinal and transverse waves. Now, further, these are some basic points that I am just reading to make you understand. Here, there is one question. Question says, given below are some examples of wave motion. State in each case if the wave motion is transverse, longitudinal, or combination of both. Motion of a kink in a longitudinal spring produced by displacing one end of the spring sideways. So here what happens? Motion of kink. So kink will have both type of motions. One is transverse, means two types of waves will be there, transverse as well as longitudinal. Second is waves produced in a cylindrical containing a liquid by moving its piston back and forth when it is compressed and then moved up. In that case, longitudinal waves will be produced. And then third point is waves produced by a motorboat sailing in water. So it will be both transverse and longitudinal. And last point is ultraviolet waves in air produced by a vibrating quartz crystal. So they will be only longitudinal because the direction of propagation, wave propagation and the motion of the particles, means vibration of the particle, will be along same line. Now, displacement relation in a propagation wave. So here we are going to see the standard equation. How do we write? Y, displacement at any time, as a function of x and t, is equal to a sine kx minus omega t plus phi. Here a is amplitude, k is 2 pi by lambda called propagation constant, omega is 2 pi by t, and phi is initial phase. Right. Here the term phi in the argument of sine function, argument means angle, argument of sine function means equivalently that we are considering a linear combination of sine and cosine functions. Here if you expand it, so what do you get? If you apply formula sine a plus b, you will get sine a cos b plus cos a sine b, etc. So we can say that the same thing we can write y function of x and t, a sine kx minus omega t plus b cos kx minus omega t. So sine function and cosine function both are used. So here further if we simplify, so in order to get amplitude we can write a square root of a square plus b square. So we will get this thing, and further we can solve to get phi, that will be tan inverse b upon a. So this thing you have understood. Here the one important point is given to understand y equation. This 14.2 written this represents a sinusoidal traveling wave. Take a fixed constant, say t equal to t0. If you write t equal to t0, then the argument of the sine function in equation 14 point is simply here. This becomes t0. Then it will become kx plus constant. Thus the shape of the wave at fixed constant as a function of x is a sine wave. Similarly, take a fixed location. Suppose we write x equal to x0. Then the argument of the sine wave function equation is constant minus omega t. So the displacement y at a fixed location thus varies sinusoidally with time. That is, the constituents of the medium at different positions execute simple harmonic motion. Finally, as t increases, x must increase in the position direction to keep kx minus omega t plus phi constant. So equation that we have already studied represents a sinusoidal harmonic wave traveling along the positive direction of x-axis. On the other hand, here if we change the sign, here in place of minus omega t we write plus omega t. So this will be another wave which will travel in opposite direction. So y function of x and t, a sine kx plus omega t plus phi represents a wave traveling in the negative direction of x-axis. And equation, this gives the names of the various physical quantities applying this. So here we can name the physical quantities, means we can write the meanings of each one. Yxt, this is displacement as a function of position and time. A is amplitude of a wave, omega is angular frequency, k is angular wave number or propagation constant, and this all is initial phase angle, right? Now, here different type of waves are given here. All are sinusoidal. Here if you observe one by one, so a harmonic wave progressing along the positive direction of x-axis at different times, right? So now amplitude and phase. Amplitude you understand. In given equation, suppose you are given y function of x and t, a sine kx plus omega t plus phi. So here a will be the amplitude, and phase means angle. So here same thing is explained, and here kx minus omega t plus phi appearing as the argument of the sine function is called the phase of the wave. So angle is the phase, and amplitude is written in the beginning, so that you have understood. We can put certain conditions to get like initial phase. If you want to find out, then we can put like x equal to 0 and t equal to 0, right? Similarly, other values can be found. So later on we will see by doing some numericals. So let's continue. Here we are going to see different results. The minimum distance between two points having the same phase is called the wavelength of the wave. You have already studied. Suppose you consider this point and this point, so this will be equal to one wavelength. If you consider this crest and this crest, so one complete wave you have to consider, right? So if you start from here, then you will reach here. So one wavelength, if you remember in a general way, if you see like this, suppose you draw, this wave. So here distance between two crests, successive crests or successive troughs will be equal to lambda, correct? So the same thing is explained here. Now going back, so up to here you have understood. Now next thing we will do in next lecture. Thank you for watching Team Educate.